Okay, good morning, everyone, and welcome to our third session on the data conversations, the third talk for the Data Conversations Initiative. Today our speaker is going to talk on a very interesting topic on, how to adapt large language models. And this has been a hot topic. We've all been reading about it for the past year or so, but I think more accelerated focus on it for the last 3-4 months since I think it has been out. It's been making this technology has been making its way into enterprise products. A lot of interest into it, and while there's a lot of chat around how it helps NLP applications. Our speaker today is going to focus and say, hey, how can we adapt it to structured data world, right? And tabular data, etc. So I am very, very pleased and happy to invite our speaker for the day, Professor Sunita Saravagi. She needs no introduction. She's the Institute Chair Professor at IIT Bombay in the Computer Science and Engineering Department. She's a top woman AI researcher who has several research papers and patents to her credit. She's on in the organizing committee for several top conferences in this area, and her research is being actively followed. And before she was at IIT Bombay, she has been part of a visiting researcher at Google Research, at Quest Database Mining Group, as well as the IBM Almaden Research Center. So with that, very happy to welcome you today, ma'am, and over to you.
Thank you, Hima. Okay, let's get started. So large language models are dazzling the world with their bewildering performance on a wide variety of tasks. In this talk, though, we are going to zoom into a specific task of text-to-SQL text-to-SQL on private relational databases. And this task actually presents an interesting interplay between the generic versus the specific. And we are going to evaluate LLMs for this task and the challenges that lie ahead. Now, some of you might be wondering, LLMs, haven't we heard about them enough? So I'm going to quickly dismiss this part by just asking ChatGPT, a large language model, to write about its capabilities. So this is what it says. Large language models are versatile AI tools that can be trained on vast amounts of text data and can solve a diverse set of tasks. They can perform tasks such as language translation, question answering, text summarization, sentiment analysis, coding, and what have you. Turns out text-to-SQL can be thought of as a coding task where we map natural language text to executable SQL code. So here there is some slight difference though. We start with a private relational database, which is typically large. In this example, I'm showing a toy data set where we have two tables. Each table has a bunch of columns and the columns have names. So the names of tables and the names of columns together form the schema of that database. And in general, the schema can be very large, like in this unreadable diagram that I'm showing. And over the past 50 or more years, people have been getting information, updating databases and using it to solve all kinds of mission critical problems, including banking, by using a language called SQL. And it's a rather complicated language. Here you see an example of a relatively simple SQL query, which is targeted for this database to retrieve some information. Even seasoned SQL writers find it somewhat difficult to read what that SQL is trying to retrieve. Here is another example of an SQL query. Now, our goal when we try to solve the text-to-SQL parsing task is to democratize access to data by allowing end users to pose natural language queries on this database. So it turns out that SQL that was present earlier corresponds to this particular natural language utterance. So which European countries have players who won the Australian Open at least 3 times? So the users find it very natural to ask in such English, form their query. And then we would like to have the text-to-SQL parser convert it into this the nitty-gritty of SQL, which has to figure out schema and relationship of the natural language words with the schema. Lots of the intricate sub-steps will have to be solved correctly in order to generate a valid SQL for a natural language text. Now, what we are seeking to do is to solve this task using an LLM. And of course, people have tried it ever since the start of deep learning, that people have tried to cast text-to-SQL as a neural network prediction task. And many different architectures have been proposed. But right now, the rage is to have this shared network architectures, which is what is sort of exemplified by these large language models, and use this shared architecture for all kinds of tasks. So if you were to use LLMs for the text-to-SQL task, the first thing you have to do is convert this schema of the database, which consists of names of relations and the columns within that relation, into a string. So you serialize that schema, by just concatenating tables, and you choose appropriate separators, and you create a sort of a string flattening of your database schema. And then you concatenate the user query with the schema, and you encode this input. And these are typically pre-trained encoders, which are the first part of a large language model, such as T5, BART, or even GPT. And then the decoder does cross-attention magic on top of this encoded input, and it is supposed to generate the correct SQL token at a time, and that is called autoregressive decoding. Now, many LLMs have been evaluated for the text-to-SQL task. We are primarily going to focus on two settings. One, where the LLM is specifically fine-tuned for text-to-SQL generation with labeled data, example spider. This is a well-known data set which contains lots of text SQL pairs across different database schema. So you take your pre-trained LLM, which has been trained maybe for various kinds of denoising tasks, and then you fine-tune it for the text-to-SQL task. The second, which is what you're going to call as unknowns, whether they have been trained for text-to-SQL, we don't know, because it's all a big mystery whether models like ChatGPT have seen text-to-SQL data. Most likely they have, but they have not been fine-tuned just before you use that model specifically for the text-to-SQL task. Maybe text-to-SQL was one of the tasks that they trained for amidst maybe thousands of other tasks. I know I'm just making up 1,000. And then when you use this second type of models, then you are supposed to kind of specify what is the task you are trying to solve. And there you can specify that via prompts. And there can be two kinds of prompts. One, which is the zero-shot prompting, where you would just specify the task. So actually, I'll give you examples of prompts later. You will just sort of specify the task in natural language, and of course, keep the user provided question and the schema, much like what we saw in the example earlier, or few short prompting, where you actually provide some examples of text SQL pairs along with the input. And like 1 year back, a bunch of researchers in Google had done a careful evaluation of whether large language models at that time Codex was specifically suited for converting text to SQL, whether these generic large language models, how good are they compared to another large language model, which has been specifically fine-tuned for the text to SQL parsing task. And on this table here, you see a summary of their numbers. Let's just focus on execution accuracy. And on the top, you see the set of models which have been fine-tuned for text to SQL, and the bottom, you see various generation of GPT models. And the accuracy that these fine-tuned models achieve sort of hovers around 80%, whereas the inference-only model, which may or may not have seen text-to-SQL data during training, they achieve at best 67% accuracy. Some students in my lab try to evaluate ChatGPT-3 for this task, and they created prompts like the kind you see here, where you give, like suppose you have a database with these tables, columns, and now convert the following query into SQL. And, when they ran it for the well-known Spider dev set benchmark, we were surprised to find that the execution accuracy was much lower. But whether it is fine-tuned LLMs or whether it is, inference-only LLMs, it seems like 80% accuracy on a sort of intricate text-to-SQL task is not bad. But when you dig a bit further, you find that the story is not so rosy all throughout. Several other studies have discovered that the models which have been trained on the easy Spider dataset, that they do not generalize very well to more challenging real-life dataset, which have more complex schema and SQL. So we still have a long way to go, and that brings us to the outline of my talk. I'm going to sort of broadly touch upon 5 topics at various levels of detail. First, we will talk about how we can on-the-fly adapt LLM, fine-tuned or not, with labeled text SQL pairs specifically on a particular private database that you might have. Second, we are going to talk about how you can adapt but without requiring labeled data on the private database. So very often, existing large operational database have their own SQL workload. Can you somehow use that SQL workload to do better adaptation? That's a very natural, practical question to ask. And we are going to sort of explore that topic in the second half. And then I will have just a little bit of time to kind of touch upon these 3 topics. One of how do you sort of what is the best way to prime LLMs with description to cover for cryptic schema names? How do you account for the reliability of the generated SQL? And finally, how do you handle really large schema? When in this LLM usage paradigm where you flatten the schema and just give that as input to the encoder, that only works for small database. How will it scale for large database? So clearly you will have to have a retrieval module before you can call the text-to-SQL module. So these are the 5 topics that we are going to dive into next. So first about on-the-fly adaptation with a few labeled examples. So here we are going to assume that we start with a reasonably good text-to-SQL parser, which have been trained to parse queries across several databases. For example, the Spider database actually spans like more than 200 schema. I think I got the number right, for this text-to-SQL parse, for the text-to-SQL task. And you start with one such model, but now you have your own private database and you want to instantly adapt the parser using only a few labeled examples, but without going through this asynchronous phase of fine-tuning model parameters, because fine-tuning is sort of a risky and time-consuming process. And so how can you do on-the-fly adaptation with a few labeled examples? You might be provided those examples as feedback from an end user who spots errors and corrects them. So you want to instantly adapt to the feedback which is provided by the user. So, a few researchers in not just for text-to-SQL, but for other highly related tasks of semantic parsing, for example, querying knowledge graphs, people have sort of embraced what we call this concatenation-based approach. So you have your input query X, but from your previous interaction, you have a few labeled examples. Let's say you have this small n labeled examples where you have the input question and the corresponding SQL query. Now, if you want to use these few labeled examples to improve the SQL generation for a new text, then guess what? You just concatenate those examples to the input query. and then just let the encoder of the language model handle it. So you just sort of have your LLM sequence to sequence model, which will somehow through different layers of self-attention in the transformer of the encoder will know how to extract from these hopefully related cases whatever it can learn on these examples and generate the correct SQL. And if you really want to teach it to make use of these few short labeled examples, you can also fine tune with few short. And this is what some of these earlier papers have been doing. So we evaluated this model. But before that, if you just want to take a look at what that final input prompt would look like. So suppose you have a user query like, how many singers do we have? And if you find two labeled examples which you think may be relevant for this input question, those labeled examples, both the text and the corresponding SQL, select count star from singer, and then the second labeled example, we are going to call these labeled examples as cases. And you have the second labeled example, what is the average and maximum capabilities for all stadiums, and the corresponding SQL. You concatenate all of these, and then you put your question and the corresponding schema. And that's your input. And you sort of then train the model to handle related cases in the input along with the input question and the schema. So we did a bunch of evaluations on this kind of a method, which we call the concatenation method. And we are evaluating here some kind of exact match accuracy of, and so this in this table, you see for different schema, which were unseen during training. So these are new schema, which you encounter only during deployment. And if you look at the baseline LLM, T5 is one baseline LLM, which gave us good accuracy. So if you use the baseline LLM, you see for across different schema, what accuracy you get. Observe that the accuracy could be very different for different schema. It depends on the complication of the schema and other things. And the average accuracy that you get is 56%. Now, let's say for each of these schema, you have a few labeled examples. So, so suppose what we do is, how many we assume that we have around 30 labeled examples for each of these schema. And for every test question, we will find the sort of, I think 5 or so most related labeled examples given that text question. And then we concatenate those related examples to the input query, and we study the, and we sort of run the decoder again. And this particular T5 concat decoder has also been trained with related cases in the input. And on the test data, we see like a 2.6% improvement in accuracy. Not bad. At least we got some improvement. But then, just out of a whim, we did a different experiment where, for another random set of schema, we concatenated each test question, not necessarily with a related case, but another example from the same schema, which is not related. And we were surprised to find that the accuracy dropped drastically from 74% in the baseline model, it dropped to 30%, which is more than half of the original accuracy we obtained just by inserting another example from the same case, but which may be irrelevant. Okay, so this is how fragile these concatenation-based approaches are. So that led us to explore some other methods of making use of a few labeled examples on the fly for your target query, which will allow us to have more control over how we handle those related examples. Another downside of this concatenation-based approach, which currently people are so sort of kind of starry-eyed about LLMs, they don't see, is that large prompts are very costly. So with every query, if you have to sort of encode them afresh by feeding the related cases with that query, your encoder is going to become very expensive. And recall that the self-attention architecture of encoders, their time grows quadratically with the length of the input. So that's not something you want. So therefore, we wanted to kind of explore architectures which bring in more structure and see whether if we did decoding with more structure, whether that would also allow us to do to exercise more control from related cases. Now, turns out there is a rich history of boutique architectures that generate SQL relational algebra trees, such as this one, instead of the SQL stream. So instead of just treating SQL as a sequence, you actually respect the structure of the SQL and directly generate the relational algebra tree. And this relational algebra tree generation is guided by the SQL grammar, and it is therefore guaranteed to always generate valid SQL. Unlike here, where there is no such guarantee. Of course, people have tried to fix it by having special constraint decoding, but that's expensive. And one such model is this SMBOP model, which was introduced in 2021. And we found it very helpful to kind of adapt this model to generate SQL in a more structured way by looking up related cases, which we store in a memory. And we look them up during decoding, and we do not use the related cases as inputs during encoding at all. So this is just a very quick overview of how SMBOP does a tree generation. So in SMBOP, the tree is generated in a bottom-up manner. So all SQL trees are first height balanced. And then instead of generating word by word of the SQL from left to right, you generate the tree level by level. In the bottommost level at t equal to 0, you predict, sort of generate the tables and schema columns, the schema subset, which is relevant for the input text. And also any constant database values that you have. So suppose if your query is name all the actors who are past 60, then in the first level, the ideal generation would give you name, actor, age, and 60, because these together define all the tables and columns and constants which are relevant for the SQL, which is target of this particular text. Now, in general, you will have at any time t, you will have a set of partially developed trees of length t. Now they have a method of combining all possible trees to form larger trees, to just increase the level of tree by 1. And that is where they bring in the SQL grammar. They sort of try only valid ways of combining lower level trees into higher level trees. And then you have a bunch of candidate trees. You score them using some parameters that you learn for scoring, different partially constructed trees. And that might give you a large number of candidate trees. And this is where the beam search thing comes in. So you retain only top k of the highest scoring trees. And that gives you sort of a set of candidate trees of depth t plus 1. And you do this iteratively until you have hit sort of the root node of your SQL. Now, this is just the baseline SMBOP model. But if you just use the baseline SMBOP model, and sometimes you might have errors. For example, here, for this particular query, name the actors who are past 60. The condition on age should have been age greater than equal to 60. And after the top K sort of pruning, unfortunately, the correct SQL comparison of age greater than equal to 60, even though it was a candidate earlier, is pruned away. And we will see how we can use the related examples to boost the score of correct trees so that they are retained in the beam. So what we do, we have proposed a method called struct CBR. So this paper is in AAAI. And we suppose if you have a related, just one related example. So this related example, let's call it case text, is show the directors names who are past 80. And for this particular text, we know the gold SQL, which is select name from director where age is greater than equal to 80. You observe that the words who are past is repeated between the input text and the limited label data that you have. And our goal is to use, to do proper contextual lookup from the SMBOB generation to this memory where we store all possible trees which are correct to boost the score of the correct outcome. So in this model, we are able to kind of do the lookup over with the candidate trees in the beam into this case memory. And we have to design a good similarity function to decide which subtrees score should be boosted based on what is there in the memory. And in our initial version of the system, we had designed a similarity function which would collapse all candidate subtrees in the memory and all candidate subtrees in the current beam into a single vector. So the single vector, of course, has to take into account both the input text and the current tree, and we get a single vector out of each input text and SQL pair, and then we compare the similarity of the two vectors. But then we discovered along the way that a single vector-based similarity is not adequate when the tree becomes large. So at higher levels of the tree, a single vector to represent the entire tree and the context in which this tree is correct is inadequate. So then we sort of solved a very interesting problem of how do you match trees and do it in a differentiable sort of way. So before that, just an example to show how the single vector based comparison fails. So consider this one, another input user text, which is what is the document ID with 1 to 2 paragraphs. This is an example input text, which is submitted for a particular database schema, which I'm not showing here. And then during SMBOB generation, let's say at some point in the beam, you have these two SQL trees. If you look at this SQL tree, you will find that the top tree is correct because it says that I am interested in documents which have between 1 and 2 counts, whereas the bottom tree tries to retrieve those documents which have more than 2 counts of paragraphs. It turns out for this query, there are 2 relevant cases from the limited labeled data that exists. And if you apply these 2 relevant, if you, for each of these 2 cases, you have the correct SQL, which is written below it. And when we do the single vector-based comparison, we would convert the text and the tree into a vector. Likewise, we will convert the second tree along with the same text into a different vector, and we will compare these 2 vectors vis-a-vis the vectors corresponding to the case memory. And we saw that with this comparison, we were in fact promoting the wrong tree up. That is perhaps maybe there are more similarity of the words in the text between the second case and our query question. So this was not working out very well. Although we got some boost in accuracy, we could have done better. So that led us to design a more fine-grained matching algorithm, which is based on aligning 2 trees. So suppose if I have 2 trees, so the same correct tree and the incorrect case tree, when we try to align them, so then we find that whatever is marked in red has not been aligned. And then if we sort of sum up the weights of the aligned nodes, we can get a more faithful similarity match between large trees in the context of their input text. So this particular algorithm is kind of somewhat kind of intricate. So, we developed this algorithm, which we call the C3 OT algorithm. It's like an optimal transport algorithm, which generalizes the Sinkhorn algorithm, which has been around for aligning two sets or two sequences to aligning trees. So basically, the way we sort of make it relevant to trees is we attach an edge cost whenever, say, the topological ordering which the tree requires is violated, or you could have any general edge cost. And then we formulate this tree alignment as a constrained optimization problem. And then we relax that constrained optimization problem. And the standard way in which people have been doing this relaxation in the graph matching literature, it turns out is not very good, because it gives rise to a non-convex objective even for trees. So we propose an alternative relaxation which introduces edge alignment variables like this, and then we are able to come up with an algorithm which is a blend of the Sinkhorn algorithm for some updates and a tree message passing algorithm for some other updates. And we do all these updates in the dual space, and we show that our updates are guaranteed to converge to the global optima. So, I understand that there is a lot of technical details which I've kind of glossed over here. So hopefully, we will have a paper out on this work very soon. This is still very much work in progress. And now with that approach, here we show on the same 5 schema that I had shown earlier, the updated numbers. So please focus on this last column here. And we find that we get higher accuracy than the T5 concat based approach by almost 3.8 or some percent. And notice that this SMBOB approach, which is our baseline model, which does structured tree generation, is already better than T5, which just does the autoregressive generation. Even though this SMBOB model has been built on top of Roberta base, which is a much smaller language model than the T5 3 billion model. T5, sorry, this is T5 large model. And that's one thing. But even then, we find that even on top of SMBOB, our method gives rise to higher accuracy. And when we just used a single embedding to represent a case and a tree, we got still an improvement of 3% over the baseline model. But we could get even more if we do a more careful match between trees, particularly when the trees get large. Now, the second interesting thing to note here are some ChatGPT numbers. So what you see here are ChatGPT zero-shot numbers, where if you do not give related cases, then you get around 30.9 accuracy. Whereas if you give some few related cases, exactly like the same set of cases that you give for T5 concat, if you give those same cases to ChatGPT, you also get a huge improvement in accuracy, around 11%, but still the baseline is anyway small to start with. And again, if you sort of look at the robustness of this approach by seeing how well it works in the presence of irrelevant cases. So when you run this model with irrelevant cases, we find, as I had shown earlier, that T5 concat has a huge drop, as we had discussed this earlier, whereas our method compared to SMBOB, which is our baseline on which we build our method. So that baseline was 76.2 and our method just barely moves around compared to the baseline. So if there are irrelevant cases, we can ignore them better because of something else that we do, this relevance weighting, which I did not have time to get into. And also doing this fine-grained tree alignment helped. So in summary of this particular part, I would like to conclude by saying that on-the-fly adaptation via prompts is not as effective as using a structured decoder, which is boosted with case lookups. And but how you do lookup is also very important. If you do lookup based on a fine-grained match as obtained from a tree alignment algorithm, then you can be more effective than if you just try to use the standard deep learning approach of collapsing everything into a single vector. Okay. So in the remaining 17 minutes, let me talk about just quickly over the remaining topics. Next, we are going to discuss how we can do adaptation where we do not have actually parallel data. Like so far, whatever we have done adaptation required us to have in the related examples, both the text and the corresponding SQL. In practice, you often have like a large private database. Even before people decide to be cool by providing a natural language interface to their database, they would typically have been operating for a long time and they would be processing queries through traditional SQL approach. So they would have like a large workload to begin with. So can those existing workloads be harnessed to do better adaptation of a text-to-SQL model when you do decide to provide natural language interface over your existing database? So yes, you can try to do that. And the obvious answer is to use another mechanism, maybe a neural network, to convert that SQL into text. And now we will then reduce it to that known problem, which we had already discussed in quite some detail in the first part of my talk. So basically, we are looking for methods which, given SQL logs in our target schema S, will use a SQL to text module. Now we have changed the direction and generate text queries corresponding to the input SQL. And once we have these text queries, now we are back to having full labeled data where for every SQL, we will have the corresponding text and we can adapt it using our favorite method. Now, in order for this approach to be useful, it's important that the synthetic text that we generate for every SQL needs to have, it needs to have some properties of consistency. Like, if the text is not faithful to the SQL, of course, the entire game is lost. It should be a natural, right? I mean, it should, if the, in the past, people have tried to use rule-based method where they use and kind of annotate the grammar with SQL, with text phrases, and then you can kind of generate canonical text corresponding to every input logical form using a grammar. But people have found that such synthetic text is not very useful if you want to use it to adapt to real user workload. So we want the generated text to be natural. And finally, we cannot just have very similar looking text for an SQL, because then you cannot handle the diversity of natural user workload. Okay. So when you have these three requirements in mind, then a simple approach that you might have thought of, that you will fine tune a text generation model for SQL to text. See, because now LLMs can do everything. They can convert language to code. They can also convert code to language, right? So you can give the SQL and you can get text out of it. They can generate comments for codes. So therefore, people, even before the ChatGPT kind of model came along, people have been trying to use the special models to convert SQL to text. And then if you want diversity, the answer has been to use sampling. And there has been quite a lot of research on how to make sure that if you want from your sequence to sequence model, not just the top one output, but if you want sort of a set of K diverse outputs, then how should you generate those diverse outputs? And methods like nuclear sampling and top K sampling, which are specifically designed to introduce diversity, have been proposed. We found in the text-to-SQL, in the SQL to text world at least, the diversity that they induce was not at all helpful. In fact, we did this one study where we evaluated a bunch of existing methods. So you see L2S, GASP, Snowball. These are 3 previous methods which have tried to train models for SQL to text conversion by fine-tuning LLMs like T5 and BART for the task. We evaluated them on diversity, which we evaluated by 100 minus self-blue. And in the natural data, the diversity was like 70, but in the workload, synthetic workload that they generated, the diversity was not even touching 3. So quite pathetic as far as diversity is concerned. So now, so what can you do about getting more diverse output? And, so some other studies have shown that LLMs fail to generate diverse text if you also simultaneously care about consistency or faithfulness. Because if you sample high probability tokens, then you will get very similar tokens. And if you sample low probability tokens, you will have diversity, but you will get inconsistent generations. So, so how can we sort of get LLMs to produce consistent but diverse text? So, we struggled with this question for a long time. And, the solution that I'm going to present might sound obvious, but it took us a while to get there. So the solution that we proposed was that when you ask for SQL to text generation, you provide a template of text that you want. So and now I will soon tell you how to get those templates. So for you will not just give the SQL, you will give the SQL and you will give a bunch of templates. These are sort of different templates. And these are not synthetic templates. I will soon get to that, unlike in rule-based systems. These templates are also obtained in a data-driven manner. And when you pair up the SQL with a template of the text that you want, insofar as the input template is diverse, you can get very diverse output sentences. So I'll get into more details soon, but we found that with this method, we got much higher diversity, like almost 34, compared to what earlier methods, which were trying to obtain diversity just by sampling tricks got. But in order to sort of complete the story, I have to answer 2 questions. One is, how do we obtain templates for a given SQL queue? And also, how do we fine-tune these T5 or BART kind of models for template filling? So, we are going to give an SQL and a template, and we want this model to essentially fill in the template. So how do we get training data for doing this filling up of the template? So I will just answer quickly the first question. So our answer to getting templates, not surprisingly, is to retrieve similar text SQL pairs from the training data. So we convert a given SQL QS to diverse natural language text query as follows. First, we take the text SQL, our target SQL, and we use the training data, because in the training data we already have text SQL pairs for many different schema. So as long as we retrieve other SQLs which might be from a different schema but which more or less have the same structure, so we use sort of structure preserving tree edit distance, in the sense that we ignore the names of tables and columns and just check whether the skeleton of the SQL matches with regard to tree edit distance. And there is not too much variety in the structure of SQLs that is there. So therefore, for most SQL structures, you are able to find a large number of near neighbors. And for each of those near neighbor SQL structure, we have, because it's labeled data, we have the corresponding text. And then all that we have to do is mask out from the text of this particular SQL the words which are specific to the schema. So we mask out schema specific words. Question is, how do you do the schema specific masking? So we tried many different neural approaches, but we found a very simple frequency based masking was good enough. So essentially you mask out all the words which are significantly more frequent in one schema as against other schema. So with that, we are able to do pretty reasonable masking, and it's okay to over mask, because the template just needs to guide the generation towards sort of diverse outputs and not exactly solve the full problem. So with that, we are able to kind of get diverse templates and solve the task. And with the synthetic workload that we generate, you can fine tune the model, or you can use them in the case-based reasoning setup and get good accuracy. So as a summary of these first two modules, which were about adaptation, if we were to take a pause and think about where existing LLMs, which were based on giving the input as a string and encoding them and then generating the outputs through these autoregressive language models, were they up to the job for this very specialized task and very structurally rich task of text to SQL generation? And I would say that the answer was no. So in fact, we should sort of push for push for LLMs which allows for more control and structure in the decoding process. You cannot just push everything in the encoder via prompts. So I think the decoder needs to become richer. So even when we found even that SMBOB, which was doing tree-based generation, was more accurate, even starting from a smaller encoder than the T5 model, which was doing autoregressive decoding. When we tried to do fine-grained alignment, during decoding, that gave us better results than if we tried to just give that input, concatenated all the related cases. If we just concatenated in the encoder, we did not get very good accuracy. And even when we are doing tree alignment, if you do fine-grained structurally aware tree alignment, that is much better than converting this entire tree and the text into a single vector. So and another thing which I did not have time to get into is that it was also very important to separately judge the relevance of different parts of the tree given input and a related case along with its corresponding SQL. So this was for the first part. And even when we talked about diversity, right, you could not, it was very difficult to get diverse output just via prompts. I did not discuss those experiments. We also tried to get diverse outputs via prompts. Give me top 5 diverse SQLs. Okay, you do get top 5 diverse SQLs, but if you ask for more, it sort of becomes repetitive from ChatGPT. Whereas we are able to have greater control on diversity via templates. And those templates were obtained through a retrieval process, which required us to do masking. And when we did the masking to generate the templates, we made use of SQL and schema specific information. And what will be very interesting is if this notion of templates can be generalized to other code, sort of text to code generation tasks. What we have done for SQL, whether it can be generalized to other code generation tasks. That will be an interesting future work. Okay, so now let me just quickly kind of just jump through these remaining topics. How much time do I have? Okay, just 3 minutes. So one more challenge, one more reason why LLM-based text-to-SQL models, they do not generalize, is because they fail to match textual mentions with schema elements, which sometimes can be very cryptic. Obviously, it is much better to invest one-time effort in associating textual descriptions or aliases with schema elements than harvesting label data sets and fine-tuning. For example, this is a schema snippet. This is a schema snippet for sort of from a data set. This is called a KaggleDB data set. And it's very different from Spider, which has very sort of friendly column names and table names. Here you see column names like C14 and C15, where it is very difficult to attach it with the textual description. So what we would like to do is to associate with them the corresponding textual description, what you see at the bottom. But then an interesting question is, how should you train these models to take into account the textual descriptions also of all the tables and columns? Now you might think that, okay, what's the big deal? We can just, if we have flattened the schema, you can also attach with the schema the textual descriptions. But then several other challenges come along. Some of these are being addressed by 2 of my students in IIT Bombay. Another question is that of reliability of the generated SQL. So, for a long time, people have wanted, particularly for tasks where you are querying a structured resource rather than just asking some generic questions whose output itself is verbose. When your answer is structured, you want more accountability and reliability in the generated answer. So, in fact, even back in 2003, this insightful paper in the pre-deep learning era, even when text-to-SQL systems were extremely conservative, it verbalizes this concern well. It says that people are unwilling to trade reliable and predictable user interfaces for intelligent and unreliable ones. Okay, so they had proposed a system called precise, which would look at the input text and reject queries which they cannot precisely answer and only accept the ones for which they can provide guarantees. Now, what does this imply in the deep learning era? And in fact, this is also this is a topic of ongoing research. Several people have tried to propose interactive methods of soliciting more information from the user as required and incorporating that feedback in various ways so that you can get more reliable outputs. I have listed 3 such systems here, but I have run out of time, so I will not be able to describe them. But those are very interesting sort of areas to explore for people who are looking for challenge. 3 students in my lab also are investigating how we can sort of interact with users better so that we can sort of use the user in an efficient manner to resolve ambiguity when there is an ambiguity in the question. So finally, I would like to end with some concluding remarks that robust, generalizable, and reliable natural language interfaces to databases and services is still a long way to go. Large language models, they have taken us a long way, but they do not still solve the problem. But I should say that maybe with huge lack of confidence, maybe tomorrow we will hear of a big release which cracks this problem perfectly. But until then, that's all that I have to say. Thank you very much for listening.
Thank you, Professor. I see there are some questions on the chat, so I can read them out for you, and then I think we can open to others if there are more questions and if you have more time. So there's first question from Manish Kesarwani, which says, how well do the boosting tree scores using memory lookup generalize to unseen examples not in the memory?
No, so actually, so whatever you have in the memory, if it is related, then it will help the user query. And if it is not related, it should not do any harm. So that was the lack of generalization of the concat-based approach that we addressed by having a separate relevance module, which will decide whether a particular entry in the memory is relevant for the current text or not.
Okay, thank you. The next question is from Atri Mandal. It says that the chat GPT that you mentioned, is this based on GPT 3.5 or GPT 4?
Oh, no, it's just 3.5.
Okay, thank you. The next one is from Hiroshi Kajino, which says, how do you train a tree-based generator? Is it a fine-tuned LLM or is it trained from scratch?
Okay, good question. So the tree-based model uses a pre-trained encoder, but the decoder is very lightweight and it is trained from scratch. And it sort of does, kind of basically at each layer, it is combining trees with various operators and scoring different trees. And for scoring the trees, it again calls the encoder with the input text and the candidate trees encoded in some format.
Thank you. If there are follow-up questions, please write them in the chat. I'm just reading them out in the order they are here. The next question is again from Manish, which says, just curious, what is the complexity of the SQL that was considered in the text-to-SQL task? Was it restricted to SPJ queries? Also, can the system distinguish between count and count distinct?
Good question. So here, the Spider workload consists of 4 categories of queries. So the SPJ queries are considered simple query. No, so I think that would be considered medium queries. So there are just these queries which do not involve any join. And then the queries which involve maybe just 2 joins. And those would be medium queries. And then there are hard and extra hard queries which involve like subqueries, etc. And yes, it does distinguish between count and count distinct. And in fact, that is one place where we have found that ChatGPT kind of models fail. They don't, so this is in fact one major source of errors with sort of non-fine-tuned models. They just don't generate enough distinct And
Thank
sort
you.
of there has been studies on what are the different reasons for the failures of different text to SQL systems. And text to schema linking is definitely one reason. Figuring out joins is a big deal. And then, this distinct and all, that's another, yes.
Okay, thank you. The next question is from Himanshu. How is the accuracy evaluated here with respect to the golden SQLs that two different SQL strings can have the same semantics? So is it by
Exactly.
matching the output on the table?
Yeah, so there are many different methods of evaluating accuracy. So here in the papers that we have written, we have reported two kinds of accuracy, and that's also pretty much the trend. So one is the execution accuracy, where you actually execute the query on a database and see whether the results match. This metric would have been mostly like a solid metric to go with, except that many queries have null output. So you can always generate null by having a drastically wrong SQL. So that is one. And the other, which is what is called the exact match accuracy, is of course the exact match modified. It does not just match the SQL string. It has to understand that there has to be like a match which is cognizant of equivalent SQL strings giving rise to the same algebra. So it does those correction. It handles isomorphism. Yeah.
Okay, changing gears is a slightly different question. What would be the general advice to people who are getting started with research in the current scenario, where we see a lot of LLMs getting released every single day?
Yeah, I mean, I don't know. It's a very tough question. Some of us are also struggling with it. Yeah, so I would say maybe wait for at least one more month. I think currently, people are still trying to find their footing. And there are things I can tell you, like, okay, we want to increase the reliability. Currently the LLMs generate wrong output confidently. But, verifying the correctness of an output is a difficult task. And in general, there have been many probes which have shown that these LLMs, they do not actually comprehend your question. They dazzle us with their answer, but if you actually, if you sort of play with its mind, you can find out that it has not really understood your question the way even sort of a child can understand your question. So even in the text to SQL example, we had a situation where we asked ChatGPT, give me 8 diverse SQL corresponding to the text, and we gave a question. And from that question, it was like something like the youngest singer or something. I don't remember the exact text of the question. And in the SQL, you were expecting to get limit 1. And limit 1, which is sort of used to find the highest or the smallest, those are very common kind of questions in the spider workload, at least. And if you sort of normally, that is like the prior, almost most of the time you would expect the output to be, limit 1. And you know what it gave? Limit 8. And for a long time, we were puzzled that from where did it find the 8? And then it occurred to us suddenly after thinking about it a lot. My student tells me, oh, I had asked for 8 diverse SQLs. So it has mixed in like an earlier text it gave about wanting 8 diverse SQL to saying that in the limit I want, not the youngest speaker or something, you'll just get the 8 youngest speakers.
Okay.
So, so there is a lot of flakiness around, but in order to kind of sort of say something meaningful in the context of LLMs, I think one should just sort of wait around a little while. Sorry, that was not very helpful answer because, as I said, all of us are struggling with it.
Yeah, no, I think it's all.
For a while, perhaps stay away from the language research. Maybe just sort of work more on textual data. Maybe Indian languages. Yeah, but then maybe there must be other companies who are doing a lot on Indian languages.
Okay, we have the last two questions. So again, another one from Manish. Can you please comment on the generated SQL that got mispredicted, and if they only had subtle mistakes that could be identified via manual verification?
Yeah, I mean, manual, say, suppose a person who knows SQL can spot the mistakes. And very often the mistakes are not that subtle also. So, but as I in one of the earlier in response to one of the earlier questions, I had said that there are papers which have tried to analyze the various reasons for wrong SQL. I am happy to point you out to those papers, but roughly, one of the main reasons is that it cannot figure out the linkage between words in the text to schema in the database. And second, it cannot figure out joins, and it sometimes misses out on distinct or not distinct. Sometimes, in SQL, there is very subtle semantics attached with whether you should use inner join, outer join, subqueries. So those are subtle, which, sometimes even SQL experts might miss. So some queries are of those kinds. Other times, maybe the semantics of the aggregate function, like if you're asking for total population, the fact that you don't need to do select count star from the country table, that population is present as a field. So just sort of not understanding the correct aggregate operation is another source of error.
Okay. And final question is that did you observe the sensitivity towards input prompts, right? Like does the output SQL change when you use lowercase versus uppercase in the text, use extra spaces, use commas, use quotes in the prompt? And if you did see that kind of thing, how did you fix it?
So, for ChatGPT, we did not observe that much sensitivity for things like comma, spaces, etc. And for G5, yeah, actually, we did not experiment enough. But, depends on the variety of prompts that we are talking about. The English question that you ask, that is very important, and different prompts can give rise to different performance. And we don't know whether the numbers that we have obtained are with the optimal prompt or not. And in general, it's not possible to answer that question.
Yeah. Okay. Yeah, I think that's the end of questions. So once again, I think on behalf of everyone here, I would like to thank you again, Professor Saravagi, for this wonderful talk. It was, I think, very nicely put into separate sections, and I'm sure everyone found it very useful. And thanks everyone for joining in. We will again meet in a month with our next talk. If you have suggestions of what you want to hear more, or if you have suggestions of speakers whom we should call to the forum, please share your comments, suggestions on the Slack channel that we have. Okay, with that, once again, thank you, Professor Saravagi, and also thank you for your patience to stay for 10 more minutes and answer all the queries. I'm sure everyone found it very helpful. And yes, with that, we end the talk.
Okay. Thank you. Thanks, Seema, for having me over. Bye, everyone.
Okay. Yeah. Thank you. Bye, everyone. Have a good weekend. Bye.
Yeah.